Yes, sir. Yes.
Are you able to see my PPT?
Yes, sir.
Okay. Okay, we already discussed, few things we discussed in the quarter joint, and we discussed already what is quarter joint, what is the application, and I have shown you some of the videos. Okay, so now, few things we discussed in the last class quarter joint. Now, today we go for just recap about the quarter joint, then we move for the further design of the quarter joint. Some of the things only we discussed in the earlier class. Okay, now the quarter joint, I mean, just we discussed, or just we go through the some basics whatever we discussed, because last 2 weeks back we discussed about the quarter joint, so maybe some students forgot about that. Okay, now see here. Quarter joint, quarter joint where we are using to connect the two coaxial rods which are subjected either tensile force or compressive force. Okay, and this is a typical applications. Just a brief discussion whatever we discussed earlier we are going to do now. Then we move to the further design of the quarter joint. Even we discussed the tensile force, quarter joint, based on tensile force, how to define the diameter of the rod, how to define the figured side the diameter of the rod, and chuckered side the diameter of the rods. Even we discussed some of the shearing stress, how the shearing stress is involved in the quarter also we discussed. Anyway, we see a few minutes we discuss about this now. What are the typical applications of the quarter joint? Joint between the piston rod and the cross head of the steam engine we are using. Joint between the spindle, slide spindle and fork of the valve mechanism we are using. Joint between the piston rod and the pump rod we are using this. And the foundation of bolt we are using this quarter joint. Okay, now what is here, how in the quarter joint, the wedge quarter joint designed in the form of wedge shape. Why we are using wedge shape? Because the quarter joint principle is wedge shape action. The quarter joint principle is based on the wedge action. Okay, when we are inserting the quarter joint, due to wedge action, it will be tightly hold this quarter and tightly hold this spigot and socket, right? When you are inserting the quarter through this slot, right? And we have to apply the little hammering force. Then the wedge action tightly hold these components, socket and spigot. Okay, this is the principle of wedge action. Now, the quarter we are inserting through the narrow slot region. Narrow slot region, the slot is provided in the socket as well as the spigot. When we are inserting this should be coincide and properly oriented, right? And when we are applying the hammering force on the quarter joint, with the help of that hammering force, the spigot and socket are properly oriented and it will be connected properly. So, and the wedge action, the quarter is, one-sided tapered design. One-sided tapered design, then the cutter can be easily assembled and easily dismantled. That's what we discussed in the first class. The cutter thickness is thickness T, and the diameter width is width of the cutter is B, and length of the cutter is L. These are the important information. So while we are going to discuss the problem, okay. Now P is the just we go through this notations. P is the tensile force acting in the cutter. In the spigot rod. Spigot rod mean one end of the spigot rod, another end of the socket rod. Force is acting P. Diameter is the diameter of the each rod. This rod diameter E D, and D1 is the outer diameter of the socket. Outer diameter of the socket. This is outer diameter of the socket D1. Okay, see here. Here D1 is given. D1 is here outer socket diameter. This one. Okay, this one. See, clearly given. And D2 is the spigot diameter outside. Spigot diameter. This is solid rod, but the spigot diameter or inside diameter of the socket, because this spigot is going to be inside the socket. Hence, it means inside the diameter of the socket. Hence, this outer diameter must be equal to the inner diameter of the socket. Outside diameter of the spigot is equal to the inner diameter of the socket. Okay, and A is nothing but the distance. This is the distance here. Once we inserted the spigot inside the socket, then we are inserting the cutter. Then the distance from the end of the slot here, to the end of the spigot end. Spigot end is nothing but A. That notation is A. Okay, these are the things very essential when we are going to design the component. How much length we have to, how much dimension we have to allow based on load, based on stress condition. We need this information. And the axial distance here, once we are inserting the cutter, what is the distance between this slot? See here, this end to how much the distance between this. This is nothing but axial distance of the slot end and end the socket collar. This is dimension C. Thickness of the cutter T, and T1 is the thickness of the spigot collar. Thickness of the collar, spigot collar is T1. These are the notations we keep in mind. Okay, now one by one we discuss. This is clearly see here how the force is acting at each component. See, the force P is acting in the left side of the socket rod. Force is acting in the right side rod of the spigot rod B. Now the force component should be equilibrium for each component, mechanical equilibrium. See here, if I consider P here in the left side of the socket rod P, then here the P by 2, because of hollow section. This is hollow section. The force will be distributed P by 2. Then this component, the summation of the force is going to be 0. Then this is the component, the socket component is in mechanical equilibrium. Now I consider the spigot. The force is acting rightward direction in the rod. The equivalent force is acting in the left side of the socket end, inside the key portion, slot portion, in this portion. Then this summation going to be 0. Then this component going to mechanical equilibrium. Now I am taking the cutter. When I am taking the cutter here P by 2, do P by 2 in top because of 2 shears, hence P by 2. Because of hollow region, here how much force is acting here, the same amount of force is going to be in opposite direction. Anyway, first we consider this one portion, cutter. The cutter also going to be, summation of forces are going to be 0. Then this is equilibrium, mechanical equilibrium. When we assemble this, if I assemble these three components, spigot, cutter, and socket, when you assemble these three, especially this region, some of the forces going to be 0, or resultant force is going to be 0. For example, this P by 2 is acting rightward direction. This P by 2 acting rightward direction in the socket, but this p by 2 in the quarter acting left direction, this p by 2 quarter in the acting left direction, then sum is going to be 0. Okay, now this is the force acting in the rightward direction in the quarter. This is a force acting in the leftward direction. When we assemble, then this summation is going to be 0. Then entire system, system is mechanical system. I mean, entire quarter joint is going to be mechanically equilibrium. Then we can go for our application. Okay, now now we are going to design the component, design the dimension, or define the dimensions of the component based on the permissible stress limit or permissible load limit. Okay. Now see here, I mean, now what we discussed earlier, the actions and the reactions between the components must be equal for maintaining the equilibrium, mechanical equilibrium condition, right? Now first we discussed, already we discussed some of the component. Now first we start from tensile force on the rod. Now, first we start from the tensile force on the rod. Okay, what is the tensile force? Tensile force on the rod, I mean, sigma t is equal to p by pi by 4 d square. This is a tensile force on the rod. Okay, p by pi by 4 d square. Then we able to find out what is the d, because sigma t is given from the table, because based on the material properties, sigma t is equal to p by pi by 4 into d square. Then d is equal to we able to find out d is equal to square root of 4p divided by sigma t. 4p divided by sigma t. Okay, now this is a tensile force acting in this rod, in the spigot rod or socket rod. Now tensile force acting in this tensile failure. Now tensile failure with respect to rod. Now second case we discussed already, tensile failure in the spigot. Tensile failure is spigot. Here, see here the figure 4.13 here. This is the region. Tensile failure in the spigot. See, this is one. Now we are considering tensile force in the rod, tensile force in the tensile failure in the spigot, tensile failure in the socket. Later we are going to consider shear in the quarter, shear in the spigot, shear in the socket. Okay, then crushing. Crushing means compressive. So crushing failure due to socket, crushing failure due to spigot. That's what we are going to discuss now. I mean, these are the things already we discussed. Now, what is the tensile force in the spigot? Now, see here, this is a tensile force, but this is pi by 4 d squared, right? See here, this is the region. I mean, when we inserted this spigot inside the slot, then this is the slot, hollow slot. In this hollow slot, the keyway is there. This hollow slot, here it is there, hollow slot. In this hollow slot, keyway is there. I mean, quarter way is there in this slot. Hence, we are considering pi by 4. This diameter is d2 squared minus of d2t minus of d2t. Okay, here one small mistake it is there. I correct it now. I may be told earlier it's wrong. This should be like this. Pi by 4 d2 squared minus d2 into t, because this is a slot. This region we have to avoid, subtract. Then this is a region going to be subjected into tensile failure. Yeah. Tensile failure. Then P by sigma tensile failure of the spigot is nothing but sigma t is equal to P by pi by 4 d squared t minus d2t. I mean, from these relations, we are able to find out the diameter d2. From the relations, we are able to find out the diameter d2. And here the thickness must be given. I mean, we have to consider 0.31d. People gone through some research, then they came to know that T is a 0.31T. This is from the design data book. The value, T value from the design data book. Okay. Now I come to the tensile failure circuit. Now earlier tensile failure in the rod, tensile failure in the spigot. Now tensile failure in the socket. We come to the tensile failure in the socket. Now see, this is a region tensile failure in the socket here. Tensile failure in the socket in this region, because the socket is in hollow section. Hollow section. What is the area? This area. In the here also slot is crossing in the socket. See here. Then that's what we are observing here, the slot. Then what is the area? This cross section. This is section view. What is the area? Pi by 4 d2 squared minus d1 squared. Sorry, pi by 4 d1 squared, because bigger diameter is d1. The outer diameter of the socket is d1. Inner diameter of the socket is d2. Pi by 4 d1 squared minus d2 squared minus of d1 minus d2 into t. Because this is a d2, this is d1. This slot is presented. Hence, we have to subtract. Okay. That's what here coming. D1 minus of pi by 4 d1, pi by 4 of d1 squared minus d2 squared. Here the bracket should come here. Okay, pi by 4 d1 squared minus d2 squared minus of d1 minus d2 into t, this slot region. Now this is tensile force, tensile stress P is equal to P, sigma T is equal to P by A. This is the area given. From this relation, we are able to find out D1. This is the tensile failure in the socket. Okay, now, there are three tensile failure we have considered now. Tensile failure in rod, tensile failure in socket, tensile failure in spigot. Now we move to shear failure. Shear failure, where it is shear failure? In the key portion. See, the key portion. See, the key is inserted from top to from top direction, from top to downward direction, inserted. Then, okay, I go back again. This is here. Now, how many shear is going to be there? When the force is acting PAP in the right direction, left direction, there's shear, one shear here, another shear here, another shear. This is a double shear. The key is subjected into double shear when the force is acting in the rod. Okay. Now, hence we are considered double shear. When we are considered double shear, this is the thickness of the key. This is the width of the key. This is the thickness of the key. Now, these dimensions, we are considering with this dimension, this region is going to be subjected into shear. Hence, we are taking shear is equal to P by 2 into BT because of double shear. Okay. Now, shear in quarter. Now, next case, shear failure. Next case, we are now going to discuss shear failure in spigot end. How shear failure in spigot end? Come to the figure 4.13b now. Shear failure in spigot. See here. Yeah, up to this we already discussed. Now up to this we discussed already. Shear failure in spigot. Shear failure in spigot. This is a shear failure in spigot. 1 minute. How shear failure in spigot? Even clear understanding. Come to here. This figure I tell you here. You can understand here. This region subjected to shear because these are inserted inside the slot. Inside, it's not a slot. Inside the inner diameter of the socket. And this is a region going to be subjected into shear. What is this region? This length is A. This area, how can I find out area? This length we know A. This region, this length is A. This dimension, this diameter D. Then it is a two sides. Both sides, the two sides going to be shear. See here, this is a projectional view. You can easily understand here. Okay, A into D2. Then both sides 2 into A into D2. Both sides going to be shear. This is the shear in spigot, shear failure in spigot. Then what is the shear stress? Shear stress. I mean, tau equal to in this tau equal to in this tau equal to, oh, already I have written. Oh, up to this we discussed, I think so. Tau is equal to P by 2 into A into D2. This diameter is D2. This region, this length is A. Okay. Then 2 into A into D2. From this relation, we are able to find out what is this A. Okay, now we discussed the tensile failure for three components, for tensile failure in three components: spigot, rod, and socket. Then we discussed shear failure in the cutter. Then now we have discussed about shear failure in the spigot. Now we are going to discuss shear failure in the socket. Shear failure in the socket. Because first we discussed tensile, now we are discussing shear failure in the socket. Yeah. We come to the figure. Next figure. See here. Shear failure. Okay. Yeah, tensile failure of the socket, shear failure. Yeah, here. Now, where is the shear failure? When we insert the cutter here, see this, can please see my cursor, see my pointer. When we insert the cutter through this region, this slot, this region going to be shear failure. You may ask, sir, here may be a failure. This already we evaluated. This failure we already evaluated here in the cutter. But here the component, the socket component going to have a shear failure. Okay, this region, when we insert the cutter from the top to bottom, then shear is going to happen in this region. Now this region, see here the side view. I mean, this is a dimension, we know this inner diameter D2 because hollow portion, and outer diameter of this D4. That's what we discussed already. Then what is the area? What is this area? What is this area? I mean, D4 minus D2 into C. D2 into C. D4 minus D2 into C. Then what is the shear stress here in this region? I write it here. Up to this we discussed, I think so already. Just a minute. Now, fifth one. Tau is equal to P by 2 into D4 minus D2 into C. Okay. Now this is shear failure. From this relation, we are able to find out what is C. Okay, what is C? What is C? Now I come to the. Now we have discussed almost shear also we completed. Shear in the cutter, shear in this spigot, shear in this socket. Now we come to the crushing failure of this spigot trend. Crushing failure of this spigot. Crushing failure, where it is crushing failure is created. Come to the figure 4.1c. I come to this figure. Crushing. See, when the cutter is going to insert it through this region, through this slot, right? Now, when the cutter is inserted through this slot, then this region of this spigot going to be crushing due to compressive force, compressive stress, right? That's what we are saying. This region is crushing. Then, if we extend this region, what is this region? This region, what is the area of this region? D2 into T. D2 into T. Now, what is this D2 into T? What is the crushing stress? Sigma C is equal to the load acting P by D2 into T. This region. Okay, this region. Now, similarly, I would like to find out the crushing failure of the socket end. Crushing failure of the socket end. From this relation, we are able to find out the thickness, or we are able to find out the D2. Able to find out the D2, or we can use for verifying our crushing failure, crushing stress is within the limit or not. Later, once we are going to the problem, you can understand. Either we can define the dimensions if the suppose the parameters are given. If the parameters are given, we able to check the crushing stress is within the permissible limit or not. That also we can do. Now, crushing failure in the socket. Now, crushing failure in the socket. Where is the come to the figure 413C, crushing failure. Now, where is the crushing failure? See here. Here, in the socket, this region, crushing failure here, right? This region. Similarly, you come to this socket, here, crushing failure going to be this region. See here, this one. Please see my pen here. I am noting down. Okay. It may be 1 minute. Here is this. I put a pointer. You can easily understand. This region. This you see here. This is the this region. This region. Can draw it here. You are you able to see here this region? That region. Okay. That region we are considering because this socket is hollow portion. Hence, this is the D2 diameter. Okay. D4, the bigger diameter D4. This is a D2. Okay. Then what is the area? It is a hollow portion. Then D4 minus D2 into thickness, quarter thickness, T. Now, what is the crushing stress in this region? Now, 6 is crushing stress in this region. Okay, sorry, I think 8th, I missed out here. Now, crushing stress is sigma C is equal to P by D2 minus D4 minus D2 into T. Crushing stress in this region. In this region. Okay. Now, we have discussed the crushing failure in the socket, crushing failure in the spigot, right? Now, the last one is bending failure. How it is possible bending failure? See, when the socket and spigot are tightly joined, then the power is transmitted with this shearing force. Okay. But when the socket and spigot are in loose connection, then what will happen? The bending is going to be occur. Bending is occur inside the carter. Okay. That's what. If the socket and spigot are tightly joined, then shear is developed. But when the socket and spigot are connected loosely, then bending occurs. Bending occurs in the carter. Now see here, this is important one. Here is this. Now see here. See, this is the uniform. This is, the force between the socket and the carter assumed very linear. Uniformly. Sorry. Here I'm talking about this. First I mentioned this. Here, uniformly distributed force between the carter and the spigot. I tell you the 3-dimensional view, then you can easily understand. See, come here, 3-dimensional view. Where here, this side, the uniform force is acting. Uniform force is acting here. Okay. Uniform force is distributed from the socket to carter. Uniform force distributed between the carter and spigot. Sorry, not socket. Spigot and carter. Uniform force is distributed spigot and carter, between the spigot and carter here. Just you turn this diagram. just turn this diagram vertical. When you turn this diagram vertical, how it will be? Is going to be, the quarter is going to be like this. Going to be like this. That's what we are presenting there, like this. When you turn it to vertical, just this figure turn to vertical. Okay, now the force is acting, uniform force is acting here in the between the uniform force is distributed between the quarter and spigot. Now come to here. We already know the force is acting here P by 2. This is P by 2. Where it is acting P by 2 here? The P by 2, the force between the socket end here, socket end and the quarter assumed to be varying linearly from 0 to maximum. 0 to maximum in that sense, I mean here the force is here. Now I turn this figure 90 degree vertical direction, then you know where P by 2 is acting here. See here, the P by 2 is here. The P by 2 is acting like this. This is here maximum amplitude, this is maximum amplitude, then uniformly distributed. Uniformly distributed. Because here maximum force, but here minimum, here 0. Here 0. This is uniformly distributed. Here, sorry, uniformly varying. Uniformly varying. Here, this region only uniformly distributed. This region is between spigot and quarter. This region is between the quarter and socket. Is uniformly varying. It's a triangular distributed force. Please keep in mind. While now we are going to use this force component to find out the bending moment in this quarter now. Okay. Yeah, just what I told earlier, please imagine it. Turn to vertical direction. This is the force between the spigot and the uniform force distributed between the spigot and quarter. This is the uniformly distributed force. Linearly distributed force maximum at the inner side, and outer of the quarter going to be linearly varying to 0. Because the quarter top portion, this is a top portion, this is a bottom portion. Here no force. Okay, hence I am considering uniformly varying. Then now this is the diagram. This is the diagram for now. Simplified force diagram. This diagram is a simplified force diagram. This one is simplified force diagram from the top one. Simplified force diagram from this. Okay. Now see here. What is Z here? The Z is nothing but average distance from the center of the from the center. Now I'm assuming this is Z distance, average distance from the center. Then what is the center now? We know this is a dimension because this quarter is now sitting on the spigot and socket. Now the quarter length is always greater than D4. That is true. Quarter length always greater than D4. Okay. Now hence, but you take this anyway. One more time, I repeat here. Now turn this quarter now. Turn this system in vertical direction. This is the diameter D4. This is the diameter D2. That's what we are pointing out. This is the length of the quarter. Length of the quarter is greater than D4. Okay. Now come to here. Now this is the D2 dimension. D2 is nothing but a socket diameter. This is the D4. D4 is the outer, the collar diameter of the socket. Now some of the things I erase it here. Now you might have been understood. Now what is this Z also I told you. Now Z is average distance. Z is nothing but average distance from the center. This is center. What is center here? How can I consider Z? Z is nothing but center to this distance. What is this distance? D by 2. D2 by 2. This is d2 by 2 average center distance. From this distance I'm saying d2 by 2. Then average distance z is I'm considering average distance divided by 2. Divided by 2 is equal to z. Please keep in mind. Now, what is this y? I mean, why I'm introducing y? Because now the downward force is, hence this is a p. This is a uniformly distributed force. I am considering this side average distance from the center distance, this side p by 2, this side p by 2 average force, then going to be total force going to be p. Now, similarly, this force I am considering the bottom region. Got it. Now this is looks like a beam. Looks like beam. Now, this is we know d4 dimension. This is we know the d2 dimension. Now, right? What is y? Now, simply I put on drawing for your understanding. Now, the force is acting like this, uniformly varying force. Okay, uniformly varying force. Now, in this uniformly varying force, where is this is how can I split this length now? This is the length. Then can I split this length like this? L by 3. This is 2L by 3. When you studied bending moment calculations and shear force calculation, you might have been studied this. L by 3 because this is a major side force. This is a minimum force 0. Then this side 2L by 3, this side L by 3. Then summation of the L by 3 plus 2 by 3. This is the total length of the beam, right? Then L by 3. Similarly, I'm considering here the X here. I mean, the force is acting here. L by 3 distance. Okay, this is L by 3 distance. Now, hence, I'm considering X here. Okay, I mean, but here total length, the total uniformly varying load is, total length of uniformly varying load is total length here, Y. This is nothing but Y. This is nothing but Y. I mean, this is the length. This is the length I'm saying Y. Okay. Now, here I considered the top one I considered is that center from the center distance. Here also my force P by 2 and this side, this P by 2 acting in the distance of X. This P by 2, this side also acting the distance of X. Okay. I mean, based on this calculation, based on this concept, Now, what is the X? X is now nothing but, I mean, Y by 3. Y by 3. What is Y here? Y is nothing but, how can I find out Y? Y is nothing but D by 4 minus D4 by 2. Sorry, D4 by 2 divided by D2 by 2. That's all. See here, D4 by 2 divided by 2. Now, X is nothing but Y by 3. Then D4 minus D2, D4 minus D2 divided by 6. So simplify this, then X is equal to D4 minus D2 divided by 6. X is equal to. Okay. Now, these are the information necessary when we are going to discuss the bending moment. So now 1 minute, I erase this, then only you can easily write other things. If you have any doubt, please ask me. I stop the erase. I mean, which one I am erasing, I can stop it. Yes, I need a space to explain this. Now, taking moment about the center, from the center. Now, see here, bending moment. What is bending moment? P by 2. This is bending moment I'm taking with the center. I mean, this is a top force, right? P by 2 into here. I mean, this is I'm taking moment about center. P by 2 into D2 by X. Here, no? D2 by X, this distance. D2 by 2 plus X. This distance, X. Okay. Now, downward force is here. From the center, downward force is here. Then minus P by 2 into Z. We know already Z. What is Z? Z is equal to, sorry, I erased it. Z is equal to D4 by, Z is equal to D2 by 4. D2 by 4. Sorry. D2 by 4. Y equal to, sorry, X is equal to, we already discussed. X is equal to D4 minus D2 by 6. Now substitute here X value and Z value, substitute here. Finally, we are going to get bending moment equal to, P by 2 into D2 by 4. Okay, D2 by 4 plus D4 minus D2 by 6. D4 minus D2 by 6. This is the bending moment we are going to get. Bending moment. Okay, bending moment. Now you know I. What is this I? I is nothing but B dq by 12. B dq by 12. Here we have to consider this one. Which one we have to consider here? Here we have to consider this. Here this is T B cube divided by 12. D B cube by 12. Because we would like to find out the bending stress. Sigma B is equal to my by I, mby by I. I is dt bq by 12. Y is nothing but, don't consider this Y, please. This Y is a different. This Y is nothing but B by 2. Please don't confuse. Okay. This Y is nothing but B by 2. This Y is nothing but B by 2. This Y is nothing but B by 2. Now, from these relations, finally we came to know that sigma B means substitute this MB value, Y value is nothing but here B by 2, moment of inertia nothing but TBQ by 12. Substitute this in the sigma B. Finally, we are going to obtain this. Formula P by 2. Actually, I forgot. Okay, it is there in the next page. I show you. See here, this one. Finally, this is the bending stress. Bending stress in the bending stress in the cutter. Okay, this is the bending stress. Now, this is the short. Briefly, we have given all the concepts in single page. This is a tensile failure in the spigot end, what we discussed. This tensile failure in the spigot end. This is the tensile failure in the socket end. This is in the cutter. This is in the tensile failure in the, okay, this is shear failure in the cutter. Shear failure in the cutter. Now, this is the cross-section area also given here for your understanding. This is the shear failure in the spigot end, spigot. This is shear failure in the socket. This is a shear failure in the cutter, Now, crushing failure in the spigot. The cross-section area also given here, spigot, P by TD2. This is this crushing failure in the socket. Sigma C is equal to P by D4 minus D2 into T here already given. Okay. Now, some of the dimensions may not be given. Then sometimes we can consider this is the standard equation from the design data book. Suppose D1 is not given, you can take 1.75 D. The D is nothing but diameter of the rod. Okay, D1 is nothing but our I think, what is D1? Anyone tell me that? What is D1? D1. What is D1? Bus. What is D1?
Diameter of socket.
Yeah,
diameter of socket color.
Thank you. D2 is diameter of the spigot. This inner diameter of the socket. Okay, D3 is diameter of the outer diameter of the socket. D4 is the collar diameter of the socket. No, this is the standard value. Sometime we can follow this. Suppose if we are unable to find out from this given relations, some data is missing, then we can use this concept to find out the required dimensions of the socket, or socket diameter, or spigot diameter, or thickness of the quarter dimensions. Now here, this is the thickness of the quarter given 0.31D. See here, this is very important diagram. See, now I am correcting your papers. Many people are not drawn the plot properly. When we are asking the questions, quarter joint, you have to draw like this figure and identify the dimension clearly. Now, this way. Now we move to the next design procedure of the quarter. This is very simple. So what we earlier discussed, some confusion how to calculate how to evaluate, how to design the quarter joint. First, we consider this is a step we should follow. See here, this is we see just 2 minutes, then we go for the problem. Calculate the diameter of the rod using this relation tensile stress. This is the standard. We have to take it from the table, design table. What I have shown here, this. Okay. Now this is the calculation. For second step, we have to define the thickness of the quarter. Third step, diameter of the D2 spigot diameter from this relation based on the tensile force acting in the spigot. Here, these are the parameters we know must. Okay. And the fourth step, we have to define the diameter of the outer diameter of the socket, from the tensile failure of the socket. Here P, D2, T, and sigma 1 must be known. Now, fifth step, we have to find the collar diameter. This is given 1.5D, 2.45D from the table, from the design data book. Okay. The sixth step, the dimensions of the A and C, we have to follow this. And the seventh step, width of the quarter. The width of the quarter, we know the shearing stress in the quarter, P by, what is shearing stress? Shearing stress is equal to P by 2 BT. From this, B is equal to P by 2 tau T. Tau T, from this relation, we are able to find out the width of the quarter. Another way, we have discussed just now, the bending stress in the quarter. Then from that relation, see here, from this relations also, we able to find out the width of the quarter. This is the B is presented here. Hence, but which one is higher value that can be considered for the design purpose? Which one is higher value that can be considered for the design purpose? Now, the last couple of steps, we have to go for verifying the crushing stress on the socket, verifying the crushing stress on the spigot. This already we discussed crushing stress on this spigot. Okay. Now we are verifying that. This crushing stress, we are verifying this. Suppose crushing stress is given in the problem directly, then we are able to find out the T2 or D2 or T also. Okay. Once we are going to the problem, you can understand. Now, check the crushing stress here, crushing and the shearing stress in the socket. Now crushing here, we are checking the crushing stress and shearing stress in the spigot, either within the permissible limit or not. After calculating all the dimensions, we are substituting here for finding the crushing stress. The crushing stress is within the limit or not from the given table. Okay. Now this is the similar way, the crushing stress and shearing stress we have to find out based on already designed dimension. Then we are verifying this, finding the, when we are finding the sigma C and tau from the socket must be within the permissible limit. Okay. Now we move to the problem. Okay. This is nothing but the thickness of the collar, thickness of the collar G1. Okay. This is a table. What I told you earlier, this is a table also we can use for the finding the some parameters. Okay. Now, for example, problem this. If you take any book, this is standard procedure. Beyond that, not possible to asking. Please practice very well in these problems. There are 2-3 problems. So enough. That is so enough. Okay. Now it is required for this problem. It is required to design a cotter joint to connect the 2 steel rods of equal diameter. Each rod is subjected to an axial tensile force of 50 kilonewton. Okay, design the joint and specify the main dimension. Okay, now first step, we have to first part of the question, we have to define the material. Okay, I mean, these are the things should be given in the problem. These are the things should be given in the problem, but as an engineer you should understand. That's what they have put here. Okay, these are the things given in the problem, but selection of material. First, we have to go for the selection of material. What we discussed in the first chapter. Okay, the rods subjected to tensile and subject to tensile and tensile, and strength criterion is considered for the rod material. Okay, the cotter is subjected to shear, direct shear, and bending stress. Based on that, we have to define the cotter. Okay, I mean, the strength, therefore the strength also the criterion of material selection for the cotter. Okay, on the basis of strength of the material, 2 rods we are considering the plain carbon steel. Plain carbon steel, this is the given from the table, 400 Newton per mm squared. It should be given you in the table, given you in the problem. It will be given you in the problem, but here you have to understand as an engineer, selection of material important. Now come to the selection of factor of safety. I mean, factor of safety in this our design concept, we are not considering the initial stress due to tightening. This thing is neglected, and the stress concentration in the socket and spigot ends also we neglected. Okay, because those things we have neglected. Now, for example, when you are neglecting some parameters, then we have to go for higher factor of safety. If you are taking those parameters, we have to find out exact FOS, factor of safety. Now I'm neglecting this kind of information in my design. Hence, I'm going for higher factor of safety. Hence, I'm choosing, for example, I'm assuming that factor of safety is 6 for socket and spigot. But I'm choosing factor of safety 4 for cotter. I'm choosing factor of safety 4 for cotter because the cotter is, I mean, small component. The cotter is less price. I mean, if failure may happen, the cotter will be broken. Then the cotter can be easily replaced. It can be easily assembled. It can be easily dismantled and assembled cotter. Hence, the socket and the spigot is a complicated design. Then more price, more cost. Then it should be prevented. When we are defining the factor of safety less for cotter, while failure happening, the cotter only going to be damaged or failure occur. Then we can save our other component, socket and spigot, because cotter is less cost and easy design and easily available, and easily it can be dismantled and assembled. Hence, we are using less factor of safety for the cotter. This is a very important reason. Now I come to the calculation of permissible stress. This is a tensile stress is nothing but sigma T is nothing but SYT divided by FOS. This is standard. I mean, shearing stress is nothing but shear yield by FOS. This also standard. We already discussed 0.5 SYT divided by FOS. But only thing is we never discussed this. I think. I mean, this I don't know. I forgot. But here, crushing stress. Crushing stress is nothing but we are always considering sigma sigma C is equal to SYC, yield crushing stress divided by FOS. I mean, this is nothing but 2 into SYT, yield strength, divided by FOS. This is you have to remember this concept formula. Okay. Now these are the already given 400 Newton per mm square. This is the tensile stress. This is the crushing stress, 133.33 Newton per mm square. This is a shear stress. Now permissible stress for the cotter. Now sigma T is equal to, we know, first we come to this. I mean, this is for socket and spigot. Now I come to the permissible stress for the carter. Permissible stress for the carter, only carter is subjected into tensile and shear. Subject to tensile and shear. Now, but a crushing we are always considered, even the discussion we gone through that crushing failure we gone through only spigot and socket, not in carter. Now here permissible stress for carter, this is yield strength. I mean, from the sigma t is equal to SYT divided by Fs, and CSS is shear yield divided by FOS. Then shear yield is nothing but 0.5 times of SYT divided by FOS, because here the stress is same. SYT, SSY we are considering same because both materials are same. Spigot material and carter material are same. But the carter we are providing less factor of safety to avoid the failure in the major components. Hence, we have to separately calculate this limit, permissible stress limit in the carter. Now come to this calculate, very simple. Please cooperate. I complete this problem. What is time now? Please, what is time now?
Sir, it's already 9.
Okay, I complete this problem, please. Okay. See here, this is the first step, diameter of the rod. We already discussed step 1. We follow this step 1. Diameter of the rod we able to find out. Okay, this sigma t is already given. Use this concept 4p by pi sigma t. Diameter of the 32 mm. Thickness of the carter is nothing but standard table. T is equal to 0.31 d. Okay, now diameter of the spigot with respect to tensile. With diameter of the spigot we know the load is given. Load is given here 50 kilonewton. Okay, now we know already d. Now here d2 minus d2 squared minus d2t, then t already we know. Then from this relation we able to find out d2. Now I come to the outer diameter of the socket. This is a spigot. Now I am coming to the socket. I am following this concept. This steps I am following now. Now I am in the socket. Where is socket? Yeah, this is socket. Now socket load, tensile, based on tensile failure. This is equation based on tensile failure. Then substitute the values, given values here. We know d2 already we have found it here. D2 we know. We are going to find out only d1. Thickness already we know from the beginning's earlier step. Then we able to find out this d1 here. D1 is equal to 55 mm. Now the fifth step, this is the D3, D4 from the standard table. This is the standard table here. 1.5D or 2.4D. Take it from the steps, standard steps from the standard table. Then find out the D2, D3, D4. Sorry, D3, D4. Then this is also standard table. Follow the standard steps. C A is equal to C. You can find it out to 24 mm. Now come to the width of the carter. You take, as we discussed earlier, right? Width of the carter is nothing but we can go width of the carter. Now, yes, yeah. See here, this is width of the carter. Now, using shear stress, direct shear stress in the carter, this is bending stress occurs in the carter. Based on that, you have to define the width of the carter. Which one is maximum value that can be considered here? Width of the carter is 50 mm. Now check now everything we have done. The last two steps is verify the crushing stress and verify the shearing stress in the socket and the spigot or within the permissible limit or not. That's what our aim now. P is we know, D2 we know, and T we know. Sigma C is now we have found it. Sigma C is 125 Newton per mm square. Now, this is from the spigot. I'm following these steps here. These steps. Now I am here. Next I am going to be here. Okay. Now sigma C. Sigma C in the sigma C I have found here from this spigot. Tau I have found from this spigot. I am verifying what is the permissible limit. We already know 133 Newton per mm squared. 130 Newton per mm squared, and the tau is 33.33 Newton per mm squared. both values, whatever the values from the design, our own design, these values are less than the our permissible limit. Similarly, find out the crushing stress and shearing stress in the socket end and verify it. Now socket end equation is this. Now it is 125 Newton per mm square. Now tau in the socket end is okay already. Okay, this is figure for your convenient I put here. Okay, anyway, not necessary now. Now this is the shearing stress. Now
Excuse me,
verify.
sir.
Yeah.
Sir, can we stop here, sir? It is already 9.
Now I stop here. I stop here. That's what I'm going to stop here. Now sigma c is from the socket 133.3 Newton per mm square. Tau is 33.33 Newton per mm square. This is less than the our less. Our value is less than the permissible limit. Hence our spigot and socket are in safe limit, within safe limit of the stresses. Now this is the last step. Thickness of the collar. Spigot collar is nothing but T1 is equal to 0.45 D. T1 is 0.45 D. Okay. Now, this is what I told you. Finally, whatever we discuss, we have to identify in the quarter joint diagram. The dimension we have to identify. We have to draw the diagram clearly and identify this component dimensions in the diagram. Okay. I stop it here. Tomorrow we are going to start a knuckle joint. One more problem is there. I complete within 10 to 15 minutes. Then I go for the knuckle joint tomorrow in the next class. Okay. Yeah. Thank you for your cooperation. So now I come to the home screen. If you have any doubt, please. Any questions in the chat box? What is the quarter is what if the quarter is made in isotrapezoidal instead of wedge shape? Instead of wedge shape. Yeah, I'm in Amarnath. Are you there in the meeting? Amarnath.
Yes, sir.
See, quarter, mostly we are using, most of the applications we are using wedge shape. That's what you are studying here, wedge shape only. Even we can use a different shape, but most of the engineering components we are using wedge shape. That is if you want to go for other trapezoidal shape, we have to go for the further discussion. But we are using most of the component wedge shape quarter. Then hence in our subject we are discussing that. I agree with you, but that they again we have to go for based on wedge shape. We have to define this shear and quarter inside the crushing and shear. Those things it will be we have to discuss separately. Okay, are you clear?
Yes, sir.
On what basis the empirical relations is achieved? The empirical relations are developed by the research people. Okay, they might have been gone through FEM concept. They might have been gone through FEM simulation, and that must be verified in the laboratory, and that must be verified in the field of applications. Then only they came to know that, for example, T1 is equal to 0.31 D. It might be 95, mostly 90 to 95%. It will be universally satisfied while designing the compound thickness, quarter thickness. Hence, they are declared we can follow thickness of the quarter is equal to 0.31 D like that. Okay. This is already people gone through research using simulation. That simulation result may be verified with the laboratory test. That laboratory test may be verified with the field applications. Then they came to know that T1 is equal to 0.31 D like that, for example. So remaining things, even D3, D4 also, they might have been done like that research. Then they came to know that. Then they might have been published in research paper, journal paper. We are collecting this data from the journal paper. We are making in the form of book. This is called the data book. Now, are you clear? Amarnath? Are you clear, Amarnath? Okay, but thank you. If you have any doubt, please ask me. Now I go to attendance, then you may close the meeting. Roll number 1.
Present, sir.
Roll number 2. Roll number 2. Roll number 3. 2 options.
Present, sir.
3, 4.
Present, sir.
5.
Present, sir.
6. 6. 6. Option 7.
Present, sir.
8. 8. 6 option.